Hello everyone, welcome to another scientific video with Temperature or Productions. And today in this video, we are going to discuss about the lowest possible temperature in anywhere of this universe. The lowest possible temperature in anywhere of the universe. It is called the absolute zero. The absolute zero. And the value of it is 0 degrees Kelvin, 0 Kelvin, sorry, 0 degrees, 0 Kelvin or minus 273 degrees Celsius. 0 Kelvin or minus 273 degrees Celsius. But how do we know this? How do we know this? And why is it not possible to have minus 300 degrees Celsius or minus 400 degrees Celsius or anything below that in this universe or in anywhere of this universe? Why is it not possible to have? Why the minus 273 degrees Celsius is the lowest possible temperature of the universe? And let's discuss today in this video. Okay. First of all, we have to understand what is a temperature. What is a temperature? Temperature is an indication of the thermal energy of that any object has. The temperature is an indication of the thermal energy that any object has. The thermal energy is not existing as thermal energy in an object. The thermal energy exists as a form of kinetic energy. This form of kinetic energy is called the particle vibration. So the thermal energy exists as a kinetic energy, a form of kinetic energy, and that kinetic energy is existing in an object as particle vibrations of the object, or the particles of the object are vibrating. The particle vibration has two things, the speed and the magnitude. So at low temperatures, the particle vibrations are slow, low speeds and low magnitudes. But as the temperature goes up, in high temperatures, the particle vibration has fast movements, fast speeds and high magnitudes. Fast movements, fast speeds and high magnitudes. So but how can we prove this? How to prove this practically or experimentally? We can do a simple experiment. We can take a sample of water. We can put some pigments and we can heat it up. So as we heat the temperature, as we heat the water sample, we can see the pigments that we have dropped into the water are vibrating faster and faster and faster with high magnitudes. As the temperature goes down, they are vibrating, they are oscillating, they are vibrating with low magnitudes and low speeds. So this confirms that each and every molecule of the water are doing the same. At high temperatures, they are vibrating fast with fast movements and fast high magnitudes. At low temperatures, they are moving slowly with low magnitudes. So these things are happening. So that particular vibration, the particle vibration, defines the thermal energy of the object and also the temperature of the object. So as we remove the thermal energy from the object, what will happen? The particle vibration becomes slower and slower and slower and slower. So as we remove the entire thermal energy from the object, what will happen? The particle vibration becomes slower, slower and slower and will become zero. At that particular temperature, once we remove the entire thermal energy from the object, the particle vibration will become zero and all the particles will lump together to behave and one lump. That is called the Bose Einstein condensate. This is a special state of matter apart from the solid state, gaseous state or liquid state. This is a special state of matter, the fourth state of matter we call the Bose Einstein condensate, and that appears when there is no thermal energy to remove from the object. And at which temperature the Bose Einstein condensate will be there in the object, that particular temperature is called the absolute zero or minus 273 degrees Celsius. For a gas, particle vibrations are crucial because the entire volume of the gas is created by particle vibrations. If there's no particle vibrations of the gas, the volume of the gas is going to become zero. And from this, we can experimentally find out what is the absolute zero. What is the value of absolute zero? By checking at which temperature the volume of the gas becomes zero. But experimental, practical in lab, this is not possible. So we use Charles' law to find it out. to find this out. Charles' law says that V is equal to kT. V equals kT. K is a constant and T is measured in Kelvin, the absolute temperature in Kelvin. So K, T is measured in Kelvin. Now we can do simple. We can select two possible temperatures. Let's say 27 degrees Celsius or 300 Kelvin, and 37 degrees Celsius and 310 Kelvin. So we can take a gas sample, let's say like helium, because helium is not making any chemical bonds and it can behave most of the time as an absolute gas, as a clear gas. Okay. Absolute gas we can discuss later. What are absolute gas? But absolute gases are nicely showing this relationship of V equals kT. Okay. Because in absolute gas we do not consider the intermolecular forces or intermolecular bondings or anything like that. We consider that absolute gas has no intermolecular forces and it behaves just like particles, just free particles. Okay. Now we can select a gas sample like helium and we can increase the temperature from 27 degrees Celsius or 300 Kelvin, and we can we can find out the volume of the gas. Let's say it's V1. Now we can heat up the gas sample to 30 degrees Celsius, okay, 37 degrees Celsius. Let's say it's 37 degrees Celsius means 310 degrees Kelvin. Now we can find out what is the temperature. Let's say, what's the volume? Let's say the volume is V2. The volume is V2. Now we can find out a relationship like that. And we can stretch the graph to this side further and further and further. But to this side, we can't stretch the graph any further beyond this point. So graph comes like this, comes like this, comes like this, comes like this, and at this particular temperature, we can see that the volume of the gas is becoming zero. So as we remove the thermal energy from the gas, the particle vibrations are becoming slower and slower and slower and slower and slower. The temperature of the gas is becoming lesser and lesser and lesser and lesser and lesser. At that particular stage, once we remove the entire thermal energy from the gas, the volume of the gas is becoming zero and the gas is showing the Bose Einstein condensate, and that particular temperature is minus 370 degrees Celsius, minus 273 degrees Celsius, and we call it 0 Kelvin or absolute zero. The absolute zero is minus 273 degrees Celsius. So at this particular temperature, we don't have any thermal energy of the object any further to remove. So as we can't remove any thermal energy from the object and further, as the object don't have any thermal energy further to remove, we can't obtain any temperature below that from the object. So this case is common to anywhere of the universe. In anywhere of the universe, we can't have any further thermal energy to remove from the object at this particular temperature, and we can't drop down the temperature any further than minus 273 degrees Celsius or 0 Kelvin. And that particular temperature is called the absolute zero. So to know the truth, now you know the case, and let's see with another video same like this, similar topic very soon. And see you soon. See you again.